Good day, everyone. Welcome again to our discussions on quantitative methods with simulations and modeling. And before we start, I would like to reiterate our previous discussions about correlations in which there is a very significant connections on our next topic, right? So, and also I would like to remind also to reiterate the discussions that we had before about supervised learning or the introductions to machine learnings, and we talk about the different algorithms under machine learnings and under these we also talk about the types of machine learning such as supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. And this time, we'll be focusing on supervised learning, specifically on on regressions, and to be specific, linear regression. Right, so today we'll be talking about linear regression. So let's try first to understand the background of linear regression. Regression actually, to be specific, is an statistical method performed to estimate the level effect of independent variable denoted with x on a dependent variable as y. It helps us to estimate the contribution of the independent variable or variables for x or group of x's on the dependent variable, which is y. In other words, it is used to um, understand or describe the relationships between a set of independent variables and dependent variables. So as an outcome of regression analysis, we get a mathematical equation often as called as a regression equation. So with this, as you can see here in this equation for regression, as y as the dependent variable is equals to alpha, which is the intercept, as shown in our graph here, plus beta, which is the slope, and x as the explanatory variable or the independent variable that we wish to use as a basis to predict the dependent variable, of course, with the intercepts and the slope. Right, so moving on, linear regression actually is a basic and commonly used type of predictive analytics. And the overall idea of regression is actually, as I've said a while ago, is to determine the two things. First, does a set of predictor variables do a good job in predicting an outcome dependent variable, for example, or which variables in particular are significant predictors of the outcome variables, and in what way do they indicate by the magnitude and sign of the beta estimates or impact the outcome variable. So these regression estimates are actually used to explain the relationships between one dependent variable and one or more independent variables. The simplest form of the regression equation, as shown in this graph here or in these presentations, where y is equals to the intercept denoted with alpha plus b or beta as the slope times the explanatory variable. Okay, there are actually three measures, okay, uses of regression analysis. First, we have determining the strength of the predictors. Second is forecasting an effect. And a third is the trend forecasting. And so regression analysis is actually a predictive modeling, excuse me, predictive modeling techniques used to analyze causes and effects. It is primarily used for, okay, as I've said, predictions and forecasting, and inferring relationships between the independent and the dependent variable. Okay, so As again, linear regression is actually a regression analysis of dependent and independent variables when they exhibit a linear relationship. So linear regression is one of the most popular subset machine learning algorithms. Its popularity is due to the fact that this technique has been around for the past 200 years. It's very long, no? And is one of the most comprehensible algorithms. So linear regression is a supervised learning technique, and it assumes that the dependence of y on x of 1, x of 2, and so on until x of p is actually linear. So the goals of linear regression, if the prediction or linear regression can be used to fit a predictive model to an observed data set of values of the response and explanatory variables. Now, after developing such a model, if additional values of the explanatory variables are collected without an accompanying response value, the fitted model can be used to make a prediction of the response. So if the goal is to explain variation in the dependent variable that can be attributed to variation in the independent variables, now the linear regression analysis can be applied to quantify the strength of the relationship between the response and the explanatory variables. So a simple linear regression, as we were talking about, is also called to be a simple linear regression if there's only one independent variable. So, and mathematically, it can be represented as y is equals b of 0 plus b of 1, x of 1 plus e, where the y is the independent variable, p of 0 is the intercept. A while ago, I showed you that it's an alpha. B of 1 is the coefficient of x of 1, independent variable, and e denoted, or epsilon is denoted with error. Okay, so regression line. So regression line is a straight line that best fits the data, actually, such the overall distance from the line to the points. So available or the available variable values. So plotted on the graph is smallest. So looking into this again in the graph, the red line there is what we call as the regression line. So what are the assumptions of linear regression? So linear regression with a standard estimation technique makes numerous assumptions about the independent variable and dependent variable. So following in the list of major assumptions made by the linear regression model, such as linearity. A linear regression model assumes that the dependent variables is a linear combination of the regression coefficient and the independent variables. So the lack of perfect multicollinearity in independent variables is another one. So why is multicollinearity a problem in linear regression? Now, first, if the independent variables are not purely independent of each other, then they are correlated. And as a result, it leads to change in one variable that will actually induce the shift in associated correlated variables. Now, if they possess a strong correlation, then it is more difficult to keep one variable unchanged with the change to the other variable. So hence, this causes the problem for linear regression models to estimate the relationship between a dependent variable and independent variable, such as correlated independent variables change simultaneously. So therefore, multicollinearity reduces the power of linear regression models to identify significantly important independent variable. Right? So that's all about linear regression. Regression itself. So these are the references that I have used in this lecture. And so this time we have demonstration time using R programming. I would like to encourage everyone to recall this. Open your R programming software. Okay, so let's have first to call this to understand the things that we are going to perform during our demonstration. Okay, so what we are looking into is to substitute the value for us to be able uh, to determine what will be our model from a particular data sets or data set, for example. Okay, so let me share to you again the R program or R programming so that you will be more, you will understand further what we mean by the formulas now about linear at the same time, like our for us to be able to know how to program in R. Right? So this is our R programming environment. Okay, so let's try to clean it up. And I would like to create a new R script here. Okay, so the first thing that I'm gonna have to do is to set first my working directory to in my computer where I'm going to save everything that I will be working on. And so at this time, I will be putting it in my drive, local disk T in this folder. Okay. Right, there you go. And then I'm going to import the data that I have in that directory. So we'll be still be using the salaries. Okay. All right, so we have here our salaries. Is our table, I mean, data set salary. Okay, with the following variables such as rank, discipline, years since the PhD, year service, sex, and the salary. Let's try to import it. All right, there you go. So we have here our data set salaries. Okay, so I'll just assign the data sets to a variable D. Okay. So D now is carrying the data that the dataset salaries has. All right. So first thing to do for me is I'd like to describe, okay, what is in D. So by looking here, we have the following. We have rank in character, discipline as in character, okay, numbers for the years that service at PhD and the years that service that years at service, also a number, and sex is also a character. And as you notice, we have two levels. We have male and female. For discipline, we have also two levels, such as A and B. And for rank, there are three levels, such as professors, assistant professor, and associate professor. And then salary is also a number, continuous variables. So first thing to do is to convert we have to convert our rank, discipline, and sex into a categorical variable, right? So because they are in categories such as professors, associate professors, and assistant professors. Same thing for the discipline. While the sex, I mean, the discipline is a binomial values. I think this is A and B, but this time it's just assume that it's a categorical variable. Same thing with the sex, such as male and female. So to convert that, we are going to use a function fact. Okay, still we'll be using rank as our how to call this as our variable here in this data set. Okay, so let's convert. So we have going to just put here so that we will know what we mean by compression, right? So it's a comment, right? So convert the values values to a factor or variable, right? Okay. So how to do that? We are going to use, of course, the factor function. So we access the data sets, the rank, okay? And we are going to convert that into a factor variable. Right. All right, there you go. Let's try to run again the stream descriptions. So you'll notice our rank now is a factor with 3 levels. Okay. So proof as 1, assistant proof as 2, and 3 will be the professor. Okay, so let's do the same with the other variables such as discipline. Right. Like that. And of course, sex. Okay, so let's run the two. There you go. Now, if you are going to run again the description, so you will notice that discipline has 2 levels, such as A and B, and sex also has 2 levels. We have males and female, female and males rather. All right. So next thing to do is to visualize our what do you call this? Our data set so that we will be able to know which one is linear relationships. Okay, so let's try to visualize. So at this point, I'm going to use a library, okay, called as our pivot table. Now, if you do not have our pivot table, all you got to do is to install it here. So click install, then you write here our pivot table, then click install. So once you're done, you can actually use that. Then access that by using this functions library, the R pivot table. All right, so by using that, okay, let's try to use the R pivot table, then the data sets D. Okay. So that, so we have here. Okay, so let's try to zoom it so that we'll be able to see the entire thing, a bigger size. There you go. All right. So we have here our data. So let's try to plot, for example, rank and sex. There you go. So you have already your descriptive in table. Okay. And if you want to view this in a scatter plot, just click here, just click scatter. So there you go. So, but you cannot see that because, you know, the values actually are in categories. So let's try to change this from sex to salary. There you go. Or let's try to change that, do that. Or years in PhD, for example. Oh, there you go. So as you can see that we can observe, okay, the higher the salary, meaning the longer that you stay in with a PhD degree. All right. So how about the years in service and the PhD? There, you can see that there is also a line, right? So we can actually interchange that here. Okay. So the x-axis is your year service and the y-axis is your years in PhD. So you can see that there is a line, right? So the pattern is going up. So let's try to use these two, okay? These two variables for our what do you call this? For our linear regression, right? So let's close this. Let's go back again to our to our script. Okay, so let's try to plot first. No? So let's try to plot our data. Okay, so we have the years in PhD and our in the years in service. Of course, the data is coming from the and let's say the PCH system. There we go. There. So we have our line here, or actually we can change that. Okay. Let's try to change it. Oh, that's it. So that's what we have shown to you a while ago while using the pivot table. And let's try to create a model now. So let's try model 1 as our linear model. I'll be using a function LM or the linear model function. Right? So we have here our target variable or our dependent variable will be years in service. Okay. It's our target variable. And then the independent variable. Right? Of course, the data is coming from D. And our method will be QR default, by default. There you go. Okay. And then let's try to look into the summary. We have our, I'm sorry, let's try to put first the line, regression line. We give a line, okay, the model 1. There you go. And let's try to look into the summary. So we have model 1. Okay, so let's look at here our model. We have here the intercept, okay, the slope, and your variable. So by looking into here, the p-value is very near to 0. Okay, so what do we mean by raised to this is a power raised to negative 7, meaning to say that there will be 6 zeros, then dot, period, then 0. That's what we mean by this. Okay, and this one has also 16. So there are 16 zeros. So it's very, very near to 0. So by determining this, we could say that the years since PhD variable has a very highly significant relationships uh, in to the years in service variable. Okay, so it's really very highly significant. Meaning to say the higher the service that you are in the institution, the longer that you will stay, okay, with a PhD degree as a doctor. Okay, so the R squared, a multiple R squared, has a value of 0.82 or 75 or 82.75%. And thus adjusted R squared is 82.7 or 82.7%. Okay, so the p-value is really very far from 0. Okay, so the if statistics are 1,894 on 1 and 397 degrees of freedom here. Okay, the residuals and errors and degrees of freedom. All right, so going back here, as we have interpreted that the year since PhD has a highly significant relationship with our dependent variable, which is the years in service. Okay, so how are we going to plot this in our in our model as our equation. Okay, that's our equation. So going back to our presentations here. So remember, we have here our y. So we could say, this is copy that. Alpha is our intercept, so just substitute this one. Okay. So let's round off that one. So we have, I'm sorry. All right. Okay, so let's try. Negative 2.872. So just round it off. The beta will be 0.918. Right? Times x is our years service. Okay? Times y years since PhD. Okay, so that is our equation. Right, so we multiply that. So this is now our model. So when we predict something, for example, in this case, we will be using this as our value. So let's try to use this one, okay, in predicting our y. Say for example, okay, say for example, we have this, okay, we assign that. Okay. Our years in service should be, let's say, for example, in years of service will be like 35. So what, I mean, years in PhD. Okay, and what will be our years in service? So do that. Oh, sorry. Oops. Right, it's -2. Oh, let's try to group it. Oh, there you are. Those are pretty just special characters. All right, so there you go. Let's try to display what's the value of y. So you can say that in terms of years in service, so you have 29 years, okay, in particular. So 29 years is somewhere over here. 29 years. Okay, that's how we predict our values by using the model. Okay, so that's it for today in terms of doing linear model. Okay, thank you very much for listening, and I hope that you learned something today.